Good afternoon, everybody. Welcome to a sort of overcast but wonderful Monday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. And I made sure I didn't watch TV before class so I could fall asleep. No, that ain't gonna happen again. All right, here's the game plan for today. First of all, I'm gonna do the alcohol problem set. And next, we'll go back to ketones and aldehydes. And what I didn't do last Wednesday, I'll do today. And that's tell you an interesting story about Dr. White and ketones and aldehydes. And it is interesting. All right. And remember, always turn in your labs that are due on Wednesday. And also, there's no such thing as a dumb question. Ask in class, like now, or come to my office hours Monday and Wednesday from 5 to 6:15 on Zoom. All right, let's do the alcohol problem set. Thumbs up, people. Everybody see it on your screen? Give me a thumbs up with your emoji. Thank you, Danielle. All right, alcohol problem set. First of all, let's go through nomenclature. Number one, give the IUPAC name for the following. How do you do an alcohol? You find the longest chain, name it as an alkane, then drop the E at the end, add OL, and if it's acyclic, meaning not in a ring, you use a number, what carbon has the hydroxyl group of an alcohol. Just to remind you, hydroxy group on a hydroxy being OH on a carbon is an alcohol. So if we look at A, 3 carbons, hydroxyl group, and propane, drop the propanol. Students forget to put the 1, but you need that because the carbon of hydroxyl group could be on 2. That's 1 propanol. Now, when you're in a ring and there are no other functional groups, which is what will happen in my class most of the semester, and for alcohols totally, tea time, the carbon with the hydroxyl group is always 1. The carbon with the hydroxyl group is always 1. Everybody knows that, so you don't need a number. So this is a hydroxyl group on a carbon, 6-membered ring. Remember the cyclohexane, drop the E, alcohol, OL, cyclohexanol. Now, if we look at C, what's the longest chain with the carbon with the hydroxyl group? 4 or 1, 2, 3, 4, 5. And 5 is greater than 4. Isn't the math hard in this class? Oh, difficult beyond all imagination. Pentane, drop the E at OL. What carbon is on the, has the hydroxyl group? That always has the lowest number. Remember, only start numbering from the end of a chain. And that's on carbon 2, 2-pentanol. Oh, look, it's your old friend, the methyl group on carbon 3, 3-methyl, 2-pentanol. Now, D, we have a ring and has a hydroxyl group. Remember, when you look at a molecule, look for what's different. Whatever is not carbon or a hydrogen atom or carbon-carbon single bond, get your attention like that. And we've got a hydroxyl group on the ring, alcohol, 5 carbons, 5 benz, cyclopentane, alcohol, drop the E at OL, no number because that carbon is number 1. And on carbon 2 is an isopropyl, carbon 3 is a methyl, and therefore it's 3-methyl, 2-isopropyl cyclopentanol. Wow, that's a mouthful. But if you wanted to, and I would accept it even though this is the correct IUPAC, if you had put 2-isopropyl, 3-methyl, I'd accept that. All right, there are 2 skills for nomenclature. in organic chemistry and on my test. And the first one is, here's the structure, give the IUPAC name. The second one is, here's the name, draw the structure. And if we look at A, start from the right, move left, OL ending, alcohol, that were E, pentane, 5 carbons, and which carbon has the hydrox group of the alcohol? Carbon 2. Now I start numbering with alcohols, ketones, and aldehydes and other things from the right, because that's how I learned it. But if you started from the left, that's fine too. Now, if we look at B, cyclobutanol. OL ending alcohol, if that were E, cyclobutane, 4-membered ring. Remember, this is a ring, not a square, because we're organic chemists. And on any carbon, you put the hydroxyl group. And if we look at C, how do you do this? You start from the right, move left. Octane, OL ending tells you it's an alcohol. And if it was octane, E ending, 8 carbons. Where's the hydrox group of the alcohol? Carbon 2. Ooh, methyl, not methyl, dimethyl. Remember, di means 2, tri means 3, and they're dimethyl. Where are they? On carbons 3 and 5. Now, if we look at F, oh, by the way, I hope everybody knows the common name ethyl alcohol, also known as ethanol, is this molecule, and that's the small molecule in beer, wine, and champagne, and highly alcoholic spirits, otherwise known as vodka and Canadian Club, 2 of my favorites. That gets people inebriated when they drink too much. Do not drink and drive. Oh, I got a public service announcement in. All right, let's look at F. Start from the right, move left. OL ending, alcohol. That were E, cyclopentane, 5 carbon ring. Carbon number 1 is hydrox group. Most of you are going to put it on, like all of you on top. You could put it on any carbon. All you're doing is rotating the ring. And on carbon 3 is an isopropyl group. All right, let's look at reactions. I'm just going to do one of these for A, B, and C, because this is the only reaction that will ever be on 2 separate tests. And that is, how do you make an alcohol? React double bond with acid and water. Remember, water is HOH. You break a pi bond, 1 carbon gets H, the other gets OH, follows Markovnikov's rule. Those that have them get it, or rich get richer, the poor get poor. That's how I got taught it, one by my professor. But the carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the hydroxyl group. And if we look at B, oh, it's a ring. Did I tell you, and I think I did, Mother Nature and Dr. White love rings. Students don't. Why? Well, how many hydrogens on the carbon? Well, you have to know there's 4, yes, 4 bonds to carbon. And if we look at the bottom carbon of the ring with the methyl group on it, count the bonds, meaning the lines, 4. 4 minus 4 is 0. Count this one, the other carbon, we see 3 bonds or lines, 4 minus 3 is 1. So this one has 1, this has 0 hydrogens. And the H from the OH goes to the one with the more hydrogens, the hydroxyl group goes here. And do you break carbon-carbon single bonds? No, you don't. And that's why the ring and methyl group are still where they are. Now, if you put the methyl group where the hydroxyl group, hydroxyl or the methyl, that would be perfectly correct. All right, let's go to something a little more complex, and that's D, E, and F. That's dehydration of a double bond with sulfuric acid. Dehydration means you lose water, H2O. And if we look at F as a good example, we have hydroxyl group on a carbon, and you're adding sulfuric acid. A little triangle means heat. I also give the temperature on the test. A lot of times don't give the temperature. And a general reaction, which I just nicely wrote on there for you. Double bond, alcohol with acid and water and heat, or acid and heat, I'm sorry. You lose the hydroxyl group, OH, and an adjacent carbon with a hydrogen, carbon next door to the carbon with the hydroxyl group. Use that, and between those two carbons, you form a double bond, and it follows Zasev's rule. And let me explain Zasev's rule. If we have F, here's the hydroxyl group. I have a hydrogen on A. If I lose that hydrogen hydroxyl group, I form compound A with the X through it. If I lose the hydroxyl group and compound hydrogen B, I form compound B, this alkene. Now, Zasev's rule, the way I'm teaching it to you is you count the number of carbon atoms directly bonded to the carbons of the double bond. I'll say that again. You count the number of carbons, atoms, not all of them, just directly atoms directly bonded to the carbons of the double bond. And the one that has the most is the product you get. And if you notice, B has 3 carbon atoms directly bonded. A has 2, which larger number? Hopefully I'll pick 3. And that's why that's the answer. Now, I sort of didn't let you do Zasev's rule on E, because on the carbon with the 2 methyl groups, there's no hydrogen. So the only place it can go is this way right here. All right. If I take a secondary alcohol and oxidize it, I'll get a ketone. You lose the hydrogen here, form a carbon-oxygen double bond. Same thing here. You take a primary alcohol, oxidize it, you'll get an aldehyde, and here's what you get here. And you know something? I'm in the mood to let you have some fun too, and I'm going to share. Now, what I haven't put on, I don't think I have any on there, but any one of the problems on the problem set, you can do it yourself with the answer, what would be the starting material? On test number 2, I'll have, I think, 3 or 4 of them. If I put any more, that would be cruel, unusual punishment, which I hopefully the Supreme Court is still on outlawing for faculty to do to students. So what would be the starting material you oxidize to make that compound? And this is the fun part of organic chemistry. It's called synthesis. And as I mentioned before, synthesis is just a fancy word meaning to make. I think everybody's done. Let's take a look at this. If we look at this, and it would be 3 points each, give the starting material for the following. And the question is, what's different here? Ooh, oxygen double bond to carbon with a hydrogen and carbons I'll call R. That's my R group. It's an aldehyde. And what do you oxidize? A primary alcohol. And therefore, what's my starting material? Well, R is this isopropyl. This carbon right here is this carbon right here, which is this carbon. And that would be your starting material. Oh, let's do this again. I'm having fun. Remember, Dr. White loves aldehydes and ketones, which we're making. What would you oxidize to make that molecule? Remember, always look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, and that should get your attention like that. For those who are wondering, when I do face-to-face, no, I don't bring the whistles in. They don't leave my house. Can't be replaced, some of them. One thing I miss being on Zoom that you can't do when people aren't turning on their webcams is you can't see when they're done. So that's why I'm using the poll. Dr. White was using some organic chemistry guilt on you. All right, I think everybody's done. What's different here? Ooh, an oxygen. Double bond to carbon. Carbon's here. Bond to that same carbon with the double bond to oxygen, and carbon's here. This is a ketone. It's a cycloketone where R and R prime are connected together. And what do you oxidize? You start with a secondary alcohol. And this carbon, which is this carbon, becomes this carbon right here. So do you break carbon-carbon single bonds? No. So if I end up with a ring with 2 methyl groups, I better start with it. This carbon right here is this carbon right here, which is this carbon right here, which means it will have this alcohol. And that's how you do it. Now, next one, and I've done this reaction numerous times, lab, you take an alcohol and react it with thionyl chloride, SOCl2, you replace the hydrox group on the carbon with the hydrox group with a chlorine. And if we look at K, I have, ooh, what's different? Alcohol. We react it with thionyl chloride. You break carbon-carbon single bonds? No. And the carbon with the hydroxyl group will be the carbon now with the chlorine. And same thing for alcohol, SOCl2, replace the carbon, hydroxyl group on the carbon with the hydroxyl group with the halogen chlorine. It's only chlorine with this reagent. And why don't you try this one? What would be the product or product for the following? And I hope my barber isn't watching because I haven't been to him in almost 2 years. Hey, does it look good? I gave myself a little trim over the weekend. In fact, he's getting real good at doing his own haircut. You try and cut your hair alone in front of a mirror. Turns out the same thing you use in a chemical plant advice works good with cutting your hair. Do it real slowly and take small little pieces. Don't go massive cutting away. Luckily, the first time I tried it, I learned that lesson because I did do it small. Oh, wait, I cut all this away. No, that's natural. All right, let's do this. What's different? And what did I do here? I did the wrong example. Well, here it's oxidation, secondary alcohol. And you get a ketone. And what's R? One of these, this is R, not bad. It doesn't matter. And this is R prime. They're attached to this carbon, which still be attached to the same carbon. And now you can go up or down, doesn't matter. I'll go up. You're going to put the oxygen below too, same thing. And now let's do the problem I really wanted to do. And why don't you try this one now? And don't forget, it's your solemn responsibility. Any structure I write make sure there are only 4 bonds to carbon. If I make a mistake, let me know. I haven't, but if I do, let me know. All right, let's do this. And here I did the favorite chemistry instructor's trick on the test and put a big, scary molecule. But if it's only big and scary, you don't know how to look at it, but you do. Look for what's different. Ooh, oxygen. Remember, look for what's not a carbon or hydrogen or carbon-carbon single bond that gets your attention like that. And it's on carbons, and we're reacting with thionyl chloride, SOCO2. And you replace the hydrox group with a chlorine. That chlorine is on the carbon with the hydroxyl group. And therefore, do you break carbon-carbon single bonds? No. Here's the carbon with the hydroxyl group. I've got 2 5 across. I've got 2 methyl groups. This thing 6 months ago, you didn't know what a methyl group is. Now it's your old friend. And the carbon with the hydroxyl group now has a chlorine. I know there are 4 bonds to carbon, so I will put in my hydrogens. All right, let's get back to the problem set. Now, if you take an alcohol and react it with HX, you do the same thing, except that you can't have a double bond in a molecule because you know HX reacts with double bonds. Now, I will never do that to you on a test because that's not fair. And did I tell you I teach by my gold rule of teaching? I don't do to my students what I didn't like done to me, and I wouldn't want anything that's unfair. So if we take an alcohol reactor with HX, remember X can be chlorine, bromine, or iodine, and you replace the hydrox group with the halogen on the carbon that had the alcohol. And here, ooh, we got a ring with a lot of stuff on it, but it's really just an alcohol. And do you break carbon-carbon single bonds? No. So I have my ring with my methyl and T-butyl group. The carbon with the hydrox group now has a chlorine. And if we look at N, same thing. What do we have? Alcohol, HX. In this case, X is bromine. You replace the hydrox group with the halogen on the carbon with the hydroxyl group. And what would you react with HI to make that molecule? Your turn, 3 points each. Oh, by the way, a sad thing happened to me. Not sad, but it's how should I say it, changing of the times, and this is sad in my mind. I gave back a test to school where I teach face-to-face, and I marked the student's answer half wrong, and I underlined her answer, and I hand wrote AND. And she came up to me after class and said, Dr. White, what's this you wrote on my test? And I'd forgotten half the class or more cannot read cursive. Not that my handwriting is that bad. They just never were taught that, which is so sad. All right. Time for you to click your mouse on something. All right, I think everybody's done. So if I look here, what's different? What's not carbon? What's not hydrogen? Oh, look, a halogen on a carbon. What am I reacting with? HX. Remember, X can be chlorine, bromine, or iodine. And what do you start with? An alcohol. And you could have put a double bond, but it would get other products. This is the best way. And what's my R group? This. Am I going to break carbon-carbon single bonds? No. I ended up with 2, 4, 5 carbons. I better start with 5 carbons. The carbon with the halogen will be the carbon with the hydroxyl group. I know there are 4 bonds to carbon. And I'm done. Now, when I wrote this problem set, I realized, no, I should have given you another Zaysev's rule problem instead of reordering everything and having to redo the alphabet. Dr. White's a lazy organic chemist. I threw in another one at the end. And here we have an alcohol, sulfuric acid, heat, high heat, and that's dehydration. You lose a carbon, the hydroxyl group, and adjacent carbon, carbon attached to the carbon with the hydroxyl group, you lose a hydrogen. And between those 2 carbons, you form a double bond. And it follows Zaysev's rule, Z's rule. I used to write Zaysev when I did it on the board. I always said, did I spell this right? And I decided, why don't I just put Z and say his name to honor his great work, which it is. And here is our hydroxyl group. Where's an adjacent carbon with hydrogens A and B? And if we lose the hydrogen from A in the hydroxyl group, you form compound A, alkene. If you lose the carbon hydroxyl group from this carbon and the hydrogen from adjacent carbon B, you form compound B, this alkene, double bond. Now, Zaysev's rule, you count the carbon atoms, not all the R group, just the atoms directly bond to the 2 carbons of double bond. Whichever of the 2 choices has more of those carbons is what you get. And here in A, there are 2. They're circled. In B, there are 3. Students forget to include that methyl. By the way, fancy term that I'll never use on a test, but it just popped up in my brain. Things do pop up in my brain time to time, and that's called an exocyclic methyl group or exocyclic carbon. Exo outside the ring, cyclic. And this has 3, B has 3 carbons connect to the carbons of the double bond. A has 2, which is the larger number, and time's up. Hopefully all pick 3, and that's the product you get. And I'm done. Any questions about the alcohols problem set? Good news, I was looking at the syllabus earlier today and where we are, and we're almost back on track, even though I lost 3 hours because they started late and also because of the president's holiday. We're almost on track again. I guess like this, 2 tracks, 2 rails. Speaking about track, I'll show it to you another day. All right, let's get back to ketones and aldehydes. But before we do that, I have a Dr. White story for you about ketones and aldehydes. Now, long time ago, I started my first job in the chemical industry after getting my PhD in organic chemistry. And then I postdoc for about 1.5 years at University of Illinois, Chicago. Back then we called it Circle. They don't anymore. And I got my first job. And I started out as a research chemist, PhD chemist at this company, and then it was called Armac. and a little later on, Dutch bought it, and eventually the name was changed to AxoChemie, then AxoNobel. And about 3 years ago, that division, AxoNobel, sold, and it's now called Nourion. But anyways, so I joined this group, and it was a good sized group. It was the process and product development group, which was a great place to start. And I had a really good boss, Bob McDaniel. I still remember him. I like Bob a lot. But anyways, on Fridays, about 15, 20 minutes before everybody was going to go home, we were on flex time, which means most people started about 7:30, and about 3:30 or so, 4 o'clock, we left. So about 15 minutes before that, our group would get together in one of the two labs we had. We had about 12 chemists and technicians and, chemists like myself and some technicians. And we'd sit around and talk about whatever, sort of end the week on a nice note, everybody together. Well, back then I lived in the city, Chicago, by Loyola University, north of that. It was a nice apartment. I was a block and a half away from the beach. That was nice. Unfortunately, parking there was horrendous. And I was able to find about a half a block from my apartment, there was this condo building, and one of the people in there didn't own a car, so they rented out their garage, and I was able to get it. So in this alley, I had a garage that was about a half block walk from my apartment, and it was quite nice. And the price wasn't too outrageous to rent, and it was a good deal. Well, problem was I'd be out there at 6 in the morning to get to work by 7, and back then they didn't have the cleanup rules for dogs, and somebody's dog left the present in the middle of right outside my garage, in the middle where you open it up. And I didn't want to run my car tires over that. So here at 6 in the morning, I clean up somebody's dog's poop. Well, I started complaining about that. And one of the chemists said, don't you know what you can get from the sample room here? And first of all, any chemical company that sells chemicals has what's called a sample room. And that is where potential customers who are approved by marketing, a salesman in that area, can get free samples of our chemicals that we would make. And if you work for a company and you use some of the chemicals the company made to make new stuff or needed in your research, you just call over there and they send you some. Now, when we say sample room, every company I ever worked for, you could get anywhere from 4 ounces up to 5 gallons, depending on how good a customer you are, et cetera, et cetera. Well, what the chemist told me was, don't you know this company, our company, you can get from the sample room, because we make it, methyl nonal ketone. Now, first of all, I haven't taught you, but there are common names for aldehydes and ketones. And for ketones, if you name each R group on the carbonyl carbon double bond to oxygen, as the alkyl groups and add the word ketone, guess what? You have the common name. Now, methyl nonal ketone, nonal is the 9-carbon alkyl group, which I really didn't ask you to learn, has this structure. And this will never be on a test. And 9 carbons is a nonal alkyl group. So this is methyl nonal ketone. Also, it would be 2-undecanone, which is 11. Undecane is 11, which I didn't ask you to learn either. And I asked the chemist, who was, I picture his face, but I can't remember his name. It's been that many decades ago. But well, I shouldn't have said that. But anyways, I said, well, what's methyl nonal ketone? He said, that's the active ingredient in dog repellent. And it says doesn't hurt them, they just don't like to smell it. And if you go out and buy a dog repellent and look in, or other animal, the animal repellent said dog and animal, you'll find it's about 3 to 4% methyl nonal ketone. Well, I called over right after he said that before I went home. And the next Monday, I came to work and they had shipped over a quart, 100% active. And I took that home in a couple plastic eyedroppers. And that night before I left my garage, I put about 3 lines drop-wise in front of my garage door in the alley. And guess what? It never had a problem with dog poop again, except when it rained and washed it away. And I put another line there. And if I needed another quart, you don't use that much. So that's my methyl nonal ketone story. All right. Now, last week, I talked about the oxidation of primary alcohols, which we also went through today, to make aldehydes. I also talked about, which we went through today, it's in 2 different chapters, alcohol reactions and how to make ketones to aldehydes. If you oxidize the secondary alcohol, you'll get a ketone. Now, there's another way of making ketones. How? And that's Friedel Crafts acylation. You learn Friedel Crafts alkylation, but what's Friedel Crafts acylation? That's a way of making aromatic ketones, where one of the R groups in the ketone is a benzene ring, or other aromatic for this, I'll keep the benzene. So let's take a look at this. Now, first of all, and this I'll never ask on a test, I don't really use it except here in this class. This is an acyl group. So Friedel Crafts acylation as opposed to alkylation, take a benzene ring, and then this new molecule, which I don't have enough time to talk about really this semester, this is called an acid chloride. And it's a very reactive functional group that I've worked with. And like alkylation, you use Friedel Crafts, use aluminum trichloride. And what you do is replace one of the hydrogens with the acyl group, carbonyl, R group. Now you also get, which you don't have to put down, HCl, the H from the benzene ring and this chlorine. And you can neutralize that later on with a base. So if we look at this, you're making one of the R groups of a ketone is a benzene ring, aromatic ketone. So let's take a look at this. What would be the organic product or products? Remember, this is inorganic, and organic chemists are heavily biased against, at least I am, inorganic stuff. Yeah. But anyways, well, I shouldn't. Water is inorganic. But what do we have here? Benzene ring. What's different? Carbonyl, carbon double bond oxygen with a halogen on it, chlorine. Oops. That's not what I wanted. That's what I wanted. And we have an acid chloride, carbonyl, carbon double bond oxygen with a chlorine and R group. This is my R group, and aluminum trichloride and you get an aromatic ketone. In this case, what's my R group? Ethyl. So my product is this. And notice you have a ketone where, let's call it R prime, is a benzene ring. Aromatic ketone. Oh, that was fun. I'm going to let you have some fun. And what would be the product or product for the following reaction? 3 points each. Your turn to have fun. In case you were wondering, I'm drinking tea from the Republic of Tea. Today, they only make it around Christmas time, and I learned from last year, stock up, which I did this year. It's called Sip and Be Merry, and it's really good tea. Along with I also have my favorites during the day, my vanilla almond and my blueberry tea. And they also make another really non-black tea that's really dangerously good called hot apple cider tea. And it tastes, when you put some sugar in there, just like the inside of an apple pie, the filling. Remember, on Wednesday, I will go through the ethers and epoxides problem set. All right, I think everybody's done, so I better get to work. If we look at this molecule, what's different? Ooh, I've got two things to look at what's different. I have a benzene ring, carbon, carbon, carbonyl, carbon double bond, a halogen, chlorine, and that's an acid chloride. And we have a catalyst, aluminum trichloride. And this is Friedel Crafts acylation, where I put a carbonyl in an R group, an acyl group. Remember, this is one of those special reactions where you're making a carbon-carbon single bond, very special, very rare. What's my R group? The isopropyl group. So I have my benzene ring, carbonyl. What's my R group? Isopropyl. And that's how you do it. If I look at the clock, wow, time flies when you're having fun with alcohols and ketones and aldehydes. It's time for a break. Come back at 1:55, 5 minutes. I'm going to get up and stretch. Let's try that again. It's time to start again. This is one of my favorite whistles. Company that made this, which was from West Germany or Germany, no longer is in business. You can't get that quality. Anyways, time to get started again. And we're talking about how to make aromatic ketones by Friedel Crafts acylation, which is this reaction right here. And remember, on test number 2, there'll be a couple more synthesis. So let's practice a synthesis. And what 2 things? Instead of 2 things, let's make this 6 points. Give the starting materials for that reaction. Yeah, 3 points each. Why not? And don't forget, tonight from 5 to 6:15 of my office hour, if you need any help or would like to practice with Dr. White so you do good on the next test, come on by. Oh, excuse me. A big yawn just slipped out. This thing, 6 months ago, you'd see lines and letters on a piece of paper. Hopefully now you're seeing organic molecules. All right, I think everybody's done. Let's take a look at this. Now, in order to answer what do you start with, in this case, and on a test, if there was more than one starting material, when I took a class, we didn't have question marks. The instructor wasn't that nice, but I will tell you that. All right, what do we have? Ooh, a benzene ring, that's different. Carbonyl, carbon double bond oxygen, and carbons. This is an aromatic ketone. I have aluminum trichloride. What do I react? Benzene. Ew. Let's try that again. Benzene ring plus an acid chloride. So it's my R group, these carbons here. And therefore, what are my 2 starting materials? Benzene was one of them, plus what's our 1, 2, 3, plus a methyl group there. Then I have my carbonyl This is this, which is this. Carbon double bond to oxygen, it's got a chlorine. And I put in my hydrogens because, you know, there's 4 bonds to carbon. And that's how you do. Oh, let's do one more for fun. Let me try something I haven't done before, so I don't get that out of memory thing. All right. Let's have you try one more. And what would you get if you react those 2 things together with aluminum trichloride catalyst? Have fun. This one might be a little tricky, but let's see if you're up to it. All right, I think everybody's done. So let me get to work. What do we have here that's different? Oh, a benzene ring. We've got a benzene ring here, but a benzene ring won't react with a benzene ring. But I have a carbonyl, carbon double bond to oxygen, with a halogen in our group. That's an acid chloride. And I obviously have my aluminum trichloride catalyst here. That's my R group. And what do I get? An aromatic ketone. What's my R group? Benzene ring. So I have my benzene ring, my carbonyl, carbon double bond to oxygen, and another benzene ring. And this is called benzophenone. Now, one of the things that I'll be doing more and more as the semester continues is asking you to ask a question, why am I learning this stuff? And the obvious answer is you're learning this because someone said you have to take organic chemistry and you want to get a good grade so you can get into a program or a school. But why learn this stuff? Well, aromatic ketones have a very special property. They can absorb energy from light, specifically UV light, and they're used as a way of, one, absorbing harmful UV radiation. Where's that? Well, if you've ever used suntan lotion or sunscreen, an aromatic ketone keeps the ultraviolet light from damaging your skin and getting cancer, which is a good thing. And for many, many years, benzophenone was that ketone. And guess what? You just learned how to make it. Now, about 8-10 years ago in EU, European Union, they found that just the slightest chance this might cause skin cancer. I mean, it was tiny, but they outlawed it, and eventually the EPA did. So the manufacturers of suntan lotion and UV and sunscreen said, all right, we'll put a methyl group somewhere on the ring, and that should be different, or other things. And now that's what they're using. Does it really change it? I don't know. But the chance of getting cancer was almost non-existent. But since it wasn't zero, the EU has a law that they outlaw it, which I can understand why. Now, what other places are aromatic ketones used for? They're used to, when they absorb light, they have this energy that they can give off to form what's called radicals. And I could do a whole semester on radical, actually 2-semester grad level course on radical chemistry. But for this class, we're really not going to talk about a little in polymerization. Now, where is that important? Well, high-speed printing. They have ink. Then instead of waiting for the ink to dry, they shine a UV light on it, and that has an aromatic ketone, which causes the ink to harden or cure, as it's called. Now, how many of you have ever seen, and it's been around for a couple of years now, the nail polish you put on your nails? Notice Dr. White doesn't do his nails that often, like never, and then you put it underneath a light, and all of a sudden it's nice and hard. That's heavy, serious organic chemistry. And that light that you put your nails under activates an aromatic ketone, which then cures, which is another way of saying hardens the nail polish on your nails. I like my claws here. So why you learn this stuff? Because it's in your everyday life. All right, now let's get back to ketones and aldehydes. And it's time for carbonyl group part 2. Now, let me just remind you, what's the carbonyl? Carbon double bond to oxygen. And you should know that, how to describe with both words and a diagram what is the carbonyl group. And remember, in aldehydes, you have a carbonyl group, and in ketones, you have a carbonyl group. Ooh. So carbonyl group, which you have an oxygen, it's more electronegative than carbon. And I'll never ask that on a test. And remember, this has a pi bond and a sigma bond. And because of that, the electrons in the 2 electrons in the pi bond are a little closer to the oxygen. It's stronger. And how do we show that? Like this. Now, this is the Greek letter delta, but lowercase. And this is the capitalized delta. And in chemistry, the capitalized delta means difference. I think in math too, but in chemistry for sure. And the lowercase means little difference. Or slight difference. Therefore, when you see this, there's a slight negative charge on oxygen and a slight positive charge on the carbonyl carbon, this carbon, which is this carbon. And that has a profound effect, very profound, on the chemistry of ketones and aldehydes. And what do we mean by that? We have nucleophilic attack. Remember, organic chemists are violent. Instead of saying reacting, we say it attacks, and we really do. Occurs at the carbonyl carbon of the carbonyl group. What's that term, nucleophilic? Well, nucleo, that's like the nucleus of an atom, which has a positive charge. And phile is a lover. Audiophile, I'm an audiophile, love music. That's why I have 5 stereos in my house. Anyways, so nucleophilic attack, a nucleophile is something looking for a positive charge. And where can it find it? On the carbonyl carbon. It's got a slight positive charge. So if I'm a nucleophile, I'm looking for, where can I find a positive charge? Carbonyl carbon. I'm going to attack that. I'm also an organic chemist and use that language. Now, next 2 slides switches off until we get to a reaction. And again, nucleophilic addition to carbonyl groups. Nucleophiles, things that are looking for a positive charge, attack or bond to the carbonyl carbon of the carbonyl group. The pi bond is broken. Here this attacks and bonds to the carbon. Nu minus is one way of showing nucleophile, and the electron goes to the oxygen. Another way, if you had H plus Nu minus, the nucleophile goes to the carbonyl carbon, the H plus goes to the oxygen. See board. Well, this is good enough. All right, it's time for our first reaction. But first, something important Dr. White has to do. Everybody take a deep breath. Let it out. Take a deep breath. Let it out. Everybody nice and relaxed. Stay that way. The next 4 reactions are challenging. Relaxed. And because of that, the next 4 reactions, I will never put as a synthesis problem on a test or the final. I will ask you to give the product or products, but I won't ask you, I can do it, but I'm not going to ask you, give the starting materials. Now, turns out these next 4 reactions, Mother Nature uses some of them, and ooh, that's scary. And I'll talk about it more when we get into it. But Mother Nature used the next 2 reactions to make carbohydrates. And if it wasn't for the next 2 reactions, we wouldn't have the good things in life like Doritos, potato chips, or rice, or potatoes, or bread, or any of that with carbohydrates. So the first one is the formation of a hemi-acetal or hemi-ketal. I'll never ask you what that is, but, and my software didn't put in the carbons here. Keep your eye on the carbonyl carbon. Now I'm going to rewrite this on my whiteboard because it'll be easier for you to see. Now, before I do that, during a number of reactions, the next couple, today and Wednesday, there's something organic chemists do. Since both aldehydes and ketones give the same type of product, when R prime is hydrogen, it's an aldehyde. When R prime is carbons and hydrogen, it's a ketone. So this is a way of writing both a ketone and aldehyde at the same time. R, carbonyl. When R prime is carbons, it's a ketone. When R prime is hydrogen, it's an aldehyde. Remember, everything happens, almost everything at the carbonyl carbon. Carbon double bond to oxygen. And I'm going to do a double prime, and you'll understand why now. And if I react it with an alcohol, and this means acid catalyst, what's attached to the carbonyl carbon is still attached. And that's this carbon, which is now this carbon. But you break the pi bond, and H goes on the oxygen, and OR from the alcohol goes here. And this is the first step Mother Nature uses to make carbohydrates. And now we're getting to very interesting, exciting reactions that are more complex. Because now you have to look at two molecules. And again, ask yourself the same question. What's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? And we have an oxygen attached to carbonyl. It's got a hydrogen, and it's got an R group here. And it could have been R prime, which would be this an aldehyde, or it could have been a ketone. And what am I reacting it with? We look up here, ooh, carbon hydroxyl group, alcohol. Acid catalyst, this is acid catalyst. And generally that's usually sulfuric acid or other ones, which I'm not teaching you this semester. So what's the general reaction? What's attached to the carbonyl carbon is still attached to it. R prime or H, or HR prime, doesn't matter which way you write it, R double prime. You break the pi bond, as a hydroxyl group, OR. And the oxygen here is bonded to the carbon in the R group as the same carbon that the hydroxyl group is on. In this case, what's R prime? What's R double prime? Keep your eye on this carbon. What's attached to it? Hydrogen, which is my R prime, 2 carbons. And then I have this carbon right here has a hydroxyl group, O, and what's R? This right here. And I'm done. Remember, keep your eye on the carbonyl carbon, because that's where the fun is. And I don't know if I mentioned this, but if somebody were to come up to me and ask, Dr. White, what kind of chemist are you? And if I were being honest with them, I would only answer one way. I'm a carbonyl synthetic organic chemist. That's where all the fun is. And a number of my discoveries dealt with carbonyl compounds, carbon double bond oxygen. All right, time for you to have some fun. Remember, this reaction, I'll never give a synthesis reaction, but I will ask you give the organic product or products for the following. 3 points each. Your turn. And remember, if you need any help, always come to my office hour. All right, I think everybody's, oh, let me do the poll. Don't be lazy, Dr. White. All right, looks like everybody's done. So if I look at this reaction, let's look at the first thing. What's different? What's not carbon? What's not hydrogen? Ooh, oxygen double bond to carbon. With carbons here, I'll call that R prime. Carbons here, I'll call that R double prime. Doesn't matter which you call R prime and R double prime. Now this R prime could have been hydrogen, but it's not. And what do we have that's different here? Carbon, carbon. Ooh, hydroxy group on carbon, alcohol, H plus. And this is formation of an hemi-acetal or hemi-ketal, which I'll never ask on a test. What's attached to the carbonyl carbon is still attached to it, R prime or H, R double prime. Then it opens up to a hydroxyl group and oxygen with the R group. The R group comes from here. What's my R? This. So keep your eye on the carbonyl carbon, what's attached to it, R prime, R double prime. This hydroxyl group, this oxygen, then R. The carbon with the hydroxyl group is the carbon attached to the oxygen there. And that's the molecule you get. And right now you wonder, well, what do I do with that? Well, later on, I'll show you Mother Nature uses this reaction to make all the carbohydrates. Next time you look at a tree or a plant or anything, the cell walls are made with this reaction. Another one I'll teach you too. Oh, let's do one more. And what would be the organic product or product for the following reaction? Boy, this first semester is moving quick. We're already in the ketones and aldehydes. Almost done with it too. And remember, if you have a question, always feel free to ask. And I think it's time for me to get to work. So how do you do this reaction? You look at the two starting materials and look for what's different. What's not carbon-carbon single bond, carbon or hydrogen atom. Ooh, oxygen bond to the carbon here, carbonyl. I have carbons here and here are prime, but it could be a hydrogen, but it's not, are double prime, and that's a ketone. And this is cyclic, so R prime and R double prime are connected together. And here I have carbon, carbon, carbon. Ooh, hydroxyl group on a carbon, alcohol, acid catalyst. Oops, got carried away with my primes. I sometimes do that. And keep your eye on the carbonyl carbon, what's attached to it, still attached to it. You have now a hydrox group, oxygen, and R group. What's my R group? Here, my alcohol. And keep your eye on the carbonyl carbon, this one right there. What's attached to it is still attached to it. This carbon is this carbon. We'll have a hydroxyl group, oxygen. Which carbon has the hydrox group, the center of 3? And that's what you get. And that's how you make when, if we look down here, I'll never ask on a test, when R prime is H, that's called a hemiacetal. When R prime is carbons, that's called a hemiketal. Well, if you look at this reaction, notice we reacted the ketone or aldehyde with one molecule, or otherwise known as 1 mole of alcohol. What happens if you do it with 2? And this is the formation of acetal or ketals. And this is a second step Mother Nature uses to make things like starch or flour. So is this an important reaction? Well, if you like those things in your life, yes. So let's look at it here. I'll rewrite it on my whiteboard. And this is a reaction I'll never put on a test of synthesis problem, but we start with a ketone or aldehyde. This is my way of writing it. And now 2 molecules or moles of alcohol. And what happens is you get what's attached to the carbonyl carbon is still attached to it. And then you're going to have not 1, but 2 oxygens. And this is why you need the 2 here. Each oxygen will have the R group from the alcohol. Now, unfortunately, this is a 1 semester class. If I had 2 semesters, I'd be teaching what's called the mechanism, how this does this step by step. And I should warn you, I don't know, warn is not to inform you, that every reaction, general reaction that I show you this semester, I can write the mechanism for it. That's part of my training. So let's take this out for a spin. And I'll do this one. what would be the organic product or products for the following? Remember, this is how we and also Mother Nature make things with this type of reaction. Maybe not the specific chemicals, but this type. If we look here, what's different? Ooh, carbonyl with a hydrogen, a methyl group. And here I'll show that by carbonyl. Carbons are double prime, and our prime in this case is really hydrogen. And notice this, we've got what's here, carbon, 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 hydroxyl group, but we also have a coefficient, the number in front of the molecule, 2. And so we have 2 alcohol, acid catalyst. And will form, keep your eye on the carbonyl carbon, what's attached to it is still attached to it. And because there's 2, it tells me I have 2 oxygens, and each one has the R group from the alcohol. And the carbon with the hydroxyl group will be the carbon this OR is attached to. So if I go back up here, I have R double prime, R prime, and this R. So what's attached to the carbonyl carbon, I'll keep there, a hydrogen and a methyl group. Then notice here, you'll have 2 oxygens. And what's R? And propyl. Notice the N carbon has the hydroxyl group. And that's what you get. And there's one for you to have fun with. We're getting into some really serious organic chemistry now. Isn't it fun? Remember, keep your eye on the carbonyl carbon. That's where the fun is. Again, these are challenging reactions, but with a little practice and their practice and their practice problems, you can do it. I have faith in you. All right, let's get going. What's different? Ooh, what's not carbon? What's not hydrogen? Oxygen double bond to carbon, carbonyl. Got carbons here and here. It's a ketone, but it could have been an aldehyde. And then we're at, the number two. Two of what's this? Carbon hydroxyl group on a carbon alcohol and acid catalyst. Keep your eye on the carbonyl carbon, what's attached to it is still attached to it. That carbon now, instead of being double bond to oxygen, has two oxygens, and each one has the R group. What's R prime? Methyl. What's our double prime? It doesn't matter which of those you call R prime or R double prime, you get the same product. And then here, that's my R group. So keep my eye on the carbonyl carbon. What's attached to it? R prime, methyl, R double prime, ethyl. Then it will have two oxygens. And what's R? Ethyl. And I'm done. And that's how you do it. Oh, let's do one more.
Could you scroll up for 1 second, Dr. White?
I'll do it even for 2 seconds.
Thanks.
Remember, I got the fastest mouse wheel finger this side or the other side of the Mississippi River. Maybe I should say for the whole world, this side or the other side of the equator. Nah, I'll just stick to the Mississippi River. That's the one disadvantage of Zoom. On Classroom, I'd have this up on a blackboard, whiteboard actually, not named after me. Got it?
Thank you.
You're welcome. And here's one more for you to have fun with. All right. Who touched my clock in my office? We just started this second hour. Boy, time flies when you're having fun with ketones and aldehydes. Really does it. And don't forget, tomorrow is the first day of March. Now, I'm going to help you out. Did that help? All right, I think let's try the poll. I think everybody's done. All right, looks like everybody's done. So if I look at the first molecule right here, what's different? What's not carbon? What's not, or hydrogen and oxygen. Double bond to carbon. Notice I have carbons here and here. They just happen to be connected. This is a ketone, cyclic, where our prime and our double prime are connected together in a ring. Could have been an aldehyde, it's not. And two, that's unusual. And I have carbon on a hydroxyl group, alcohol, and acid catalyst. And what happens? Keep your eye on the carbonyl carbon, carbon double bond to oxygen. What's attached to that directly stays attached. And then it opens up that same carbon, two oxygens, and the R group from each, from the alcohol, or OR actually. So do you break carbon-carbon single bonds? No. So I still have my ring, because that's what's attached here. They're just connected together. I still have my methyl group. And then this carbon, which is this carbon, has two oxygens. And then my R group is methyl. And that's how you do it. That's an interesting looking molecule, but then I'm an organic chemist. Now, these two reactions I will never give a synthesis problem on, because that's cruel, unusual punishment. And so far, that's still outlawed by the US Supreme Court. I hope they don't change that. But anyways, these are the two reactions Mother Nature uses to make carbohydrates. And later, near the end of the semester, I think it's week, I'm guessing now, 14 or 15, I'll teach you, maybe 13, I'll teach you about carbohydrates and show you the exact chemistry. Now, the next two reactions, not to scare you, but I will, goes on in your stomach. The next two reaction Mother Nature uses to help us digest carbohydrates. I don't know about you, but when I was a little kid, like about way down here, about 2 or 3 years old, I remember my mother used to say, guess what? Chew your food before you swallow or you'll choke. And she was right. I almost did. Relax, I survived, in case you were wondering. But anyways, let's take a look at the next reaction. One more. They keep on calling when I tell them I'm teaching now. Stop. Thank you. Now stop. All right. Now, when you have a hemiacetal, or, well, in this case, a hemiacetal, you can react it with water and acid. Now, wherever you are, can you tell me real quick where you can find right now water and acid? And the answer is your stomach. And this is how your stomach breaks down the starches, carbohydrates, to gain nourishment And now I'm well beyond my level of expertise of the human body, because the last biology I took was freshman year of high school. Well, let's look at this reaction on the whiteboard. And if we take a hemi-acetal or hemi-ketal, when R prime is hydrogen, it's the hemi-acetal. I'll never ask that on a test, but I'll use terminology in the class. When R prime is carbon, it's a hemi-ketal. And we react it with acid and water, water and acid, doesn't matter which way you write it. And keep your eye on the carbon with the two oxygens. This and the next reaction are the only cases where you have two oxygens on the same carbon in a molecule in all of organic chemistry. And this carbon with the two oxygens goes back to give you the aldehyde or ketone you would have used to make that molecule. And then this part and this is a ketone or aldehyde, plus you get the alcohol you would have used to make that hemi-acetal or hemi-ketal. So essentially you reverse it. You make it, in other words, Mother Nature makes the starches and you can react them further. This is the next reaction. This reaction I'll never give you on a test or final as a synthesis problem. And let's look at the following. Give the product or products for the following. How do you do it? Well, you look for what's different. Ooh, not one, but two oxygens on the same carbon. One has a hydroxyl group that's not an alcohol. One has carbons. And on that same carbon, we have a hydrogen, but it could have been R prime, but it's a hydrogen. And we have carbons here. I'll call that R double prime. This is a hemi-acetal or hemi-ketal. You react it with water and acid. What's attached to this carbon with the two oxygens, R prime or hydrogen, R double prime are still there. And this becomes a ketone or aldehyde that you would have used to make that molecule. And then this part here becomes the alcohol you would have used to make that. So if we go back up here, this I'll call R prime, R double prime, and R. The carbon with this oxygen will be the carbon with the hydroxyl group. The carbon with this oxygen, our group here, will be the carbon with the hydroxyl group, my alcohol. So I have my carbonyl. What's our prime? Hydrogen. What's our double prime? Methyl. Then I'll have my alcohol. What's our ethyl? And there you go. And that's how you do this reaction. Oh my goodness, I went a whole minute, more than a minute into our break. I won't go over class, but I just got carried away with so much good fun. All right, I'll leave this up. Let's take a break, come back at 2:56, 5 minutes from now. I'll see you in 5. let's get back to work. I might have started a minute early, so I'll give you a little while to get back. All right. I was just thinking, maybe I should have used when I was a little kid. Did you ever play hide and seek? I think it was hide and seek when you caught someone and then you'd yell out, come out, wherever you are. Boy, that's an old memory. Fun one. All right, we're talking about this reaction where if you react a hemi-acetal or hemi-ketal of this form with acid water, that goes on your stomach, among other places, you get back the aldehyde or ketone plus the alcohol you would have used to make that. Have you noticed? I haven't given you a chance to have fun. So I better. Uh-oh, got me. I gotta close this. I'll be bringing it right back. Sorry about that. All right, slight break for you. And why don't you try this one? Let's see if you're up to it. I have faith in you guys. I have faith in my students. That sounds more professional. Your turn, have fun. Let me make this look a little nicer. There. And this is a little more complex, so take your time. I give everybody a chance to finish. All right, let's move forward and let me do this. Now, when you're looking at a molecule, now we're getting deep into organic chemistry. Look for what's different. What's different? What's not a carbon? What's not a hydrogen? Two oxygens. And notice they're the same carbon. That's very rare in organic chemistry. One's a hydroxy group, one's oxygen with carbons, R. Then on that same carbon, we have carbons here, R prime, could have been a hydrogen, but it's not, and carbons here, R, hemi ketal, if R prime were hydrogen, hemi acetal, acid and water, or water and acid. H plus means acid catalyst, H2O. I hope you all know means water. And what's attached to that carbon that has the two oxygens, R prime or H, is still attached to it. And also R double prime, and this will be double bond to oxygen. It's the aldehyde or ketone you would have used to make this compound. And then this part right here becomes an alcohol. So now that we've identified that, what's attached to this carbon, which becomes this carbon right here, R prime ethyl, R double prime ethyl. And then I'll get my alcohol, and here's my R group. And the carbon with the oxygen here is the carbon here with the hydroxyl group. 3 carbons, because you don't break, oops. Let's go back down where it should be. 3 carbons. The end carbon has the oxygen, so I'll have the hydroxyl group. And that's what you get. Oh, let's do another one. Or first of all, anybody like me to explain that again? Give me a thumbs up. All right, let's do another one. But did everybody get that copied down? All right, let's move on to one more for you to try. I think I might have made the last one a little too rough. This one's a little easier. Enjoy. Remember, look for what's different. All right, looks like everybody's done. I better get to work. So if we look at this molecule, look for what's different, what's not a carbon, what's not hydrogen. Ooh, 2 oxygens to the same carbon. One has a hydrogen, OH, the other has carbons, R. Attached to that same carbon is a hydrogen, but it could be R prime, but in this case it is hydrogen. And carbons here, I'll call that R double prime. And this is a hemi acetal or ketal. In this case, it's an hemiacetal, but I'll never ask you that on a test. And we're reacting with water and acid. What's attached to this carbon with the 2 oxygens is still attached, because you don't break carbon-carbon single bonds. That carbon will be double bond to oxygen, ketone or aldehyde, and you'll get a second thing, and that's the alcohol. And so this is the aldehyde or ketone plus the alcohol you would have used to make that, and you just get it back. So let's go up here. What's our prime? Hydrogen. What's our double prime? 3 carbons. What's our methyl? So let's go this way. What's attached to this carbon, which will be double bond to oxygen, still attached to it, R prime, hydrogen, 3 carbons. Oh, just fit that in. And then my R group on the alcohol is methyl. And that's how you do it. Now, we're getting to a part of the semester where I highly, highly recommend you do the problem sets. And don't wait until the day before a test. Do it now. And now, one other thing I haven't mentioned is, what if you want to do more of these practice problems for this reaction? How do you do that? Well, I'm going to give you a real secret of Dr. White. And if we look at carbon hydroxyl group, if I want to do specific, now, do I want to make R prime hydrogen or some carbons? I'll make it one carbon, not hydrogen. Now, our double prime, how many carbons do I want to make? Well, let's make it 3. And then I have an oxygen. And how many carbons do I want to make R? 2. I could have made it more or less. And then I'm reacting with acid and water. And that's how I make up my problems. I do this on the fly. I'm thinking, well, how many carbons do I want? And for this one, I'll do it real quick. What do we have? What's different? Hydroxyl group. OR, R prime is carbon. It could have been hydrogen. R double prime, acid and water, water and acid. Keep your eye on the carbon with the 2 oxygens. That becomes this carbon. And what's attached to it is still attached. And that's the aldehyde or ketone you would have used to make that hemi-acetal or hemi-ketal, plus this, the alcohol. R double prime, R prime, R. What's attached to this carbon here? R prime and R double prime. I think, no, I did a slightly different one. And R prime is methyl. So I get this ketone. Let's move me out of the way here. Then the alcohol right here, R is ethyl. So if you like more practice problems, you can do your own. Now, how do you know they're right? See me after class and show me, or come to my office hour and I'll tell you if they're right or wrong. Because I have a piece of paper signed by the Board of Regents and the president of Michigan State University saying I know how to do that, my PhD degree. All right, let's move on. Well, this was reversing what's also known as acid hydrolysis of a hemi-acetal or hemi-ketal. What about reversing or acid hydrolysis of a acetal or ketal? Remember the previous reaction and this one, I will never give a synthesis question, give the starting materials on a test, but I will ask you to give the product or products, and this is going on in your stomach. Woo! Organic chemistry is going on throughout your whole body right now as you learn it. And let's look at it on the whiteboard. Again, water and acid, or acid and water. I always think of one of the great miracles of life is I have and you have, in this case, H plus is hydrochloric acid. You have cells in your body, in your stomach, I think also one of your intestines, I always forget which, that actually produce HCl, H plus. It's always mind-boggling to me. Now here, this is one of the only 2 cases in organic chemistry. I just showed you the other one. This is the second one where you have 2 oxygens single bonded to the same carbon. And what you get back is the ketone or aldehyde. Remember, R prime can be hydrogen or carbons. plus the alcohol you would have used to make that. Now, as you've seen on test 1, and test 2 will be the same, it says give the product or products. Now, you don't have to balance it, but if you really have to, you could always put a 2 in front. I put it in quotes just to say that's not necessary, but if you want to, go right ahead. And if you think about it, without the 2, the previous reaction and this one gives the same products. The only difference is they're different reactions for different starting materials, but they give the same products. Oops. That was another way of showing acid and water, which I didn't want to do. And the acid is a catalyst, it just makes it go quicker. And if we look at this, how do we do it? And we look, what's different? What's not carbon? What's not hydrogen? Ooh, 2 oxygens that are the same carbon. And each oxygen has an R group, carbons on it. And on the same carbon with 2 oxygens, I have carbons here. I'll call that R prime. Could have been a hydrogen. And carbons here are double prime. And when you add acid and water, you undo this and you get back the aldehyde or ketone you would have used to make that. And this carbon, the carbonyl carbon, is this one. And you get back the alcohol you would have used to make that. And for those who must, can I write it any smaller? You can always put the 2 there, but it's not necessary, which is why I put it in quotes. So what's R prime? What's R double prime? What's R? Keep your eye on the carbon with the 2 oxygens, becomes this carbon. And what's R? Methyl. What's R prime? Methyl. And what's my alcohol? Here's my R. The carbon with the oxygen is the carbon with the hydroxyl group. And for those who must, let's see how small I can make it. You could put a 2 in front of that alcohol. You don't need to. And that's how you do it. And I'll hold down while you write down because I'm doing more complex structures now. Oh, tonight at midnight, I'll be giving speed structure drawing lessons. No, I won't. Yeah, I think, is everybody done? Okay, let me have you try one. And there you go. Boy, I'm so glad I learned about this tablet 2 years ago and discovered how you can use Microsoft Word with the tablet to look like I'm drawing on a whiteboard in a class. It's been almost 2 years. Should be interesting what's happening in the coming days and weeks ahead in our country. Not only what's happening in Ukraine, but at the other school I teach at, when I got there this morning, they had new signs up that masks are optional. I had mine on, I'll keep it on for a long time, but they still, like ECC, require everybody to be fully vaccinated or meet the testing routine. Protocol, not routine. Not to get into politics, but for those who are following the news, looks like our president did a wise thing in terms of the sanctions, because it's really hurting Russia. And the way he brought the rest of the world together to help combat the aggression in Ukraine is quite amazing to see. And hopefully it works quite well. Hopefully Vladimir Putin realized he stuck his face into a hornet's nest. Enough of my personal opinions. Remember, this is all nucleophilic attacks on the carbonyl carbon, or in this case, undoing it to get back what you started with. All right, looks like everybody's done, so I better get to work. If we look at this molecule and look for what's different, we see what's not carbon, what's not hydrogen, oxygen here, the same carbon. That only happens twice in all of organic chemistry. And each oxygen, their carbons are. And on that same carbon, right here, there's a hydrogen, but it could have been carbons. And we have carbons here. So this is our prime. This is our double prime. And what do you get when you react that with water and acid? You get back the aldehyde or the ketone you would have used to make that. Here's that carbon, plus the alcohol you would have used to make this ketal or acetal. And for those who must, you can put the 2 in front of there. So I'm going to start with this carbon. What's attached to it? Carbon or hydrogen single bonds. R prime and R double prime are still attached, and it's the carbonyl becomes an aldehyde. Then what's my R group? Methyl, which means I have this alcohol. And for those who must, I started doing that because a number of years ago, I had these 2 twins, and they got really upset when I didn't put the 2 there. I mean, really upset. The last thing I need is an upset student. Oh, let's do one more. Let's have fun with this. And there you go. What would be the organic product or product for the following reaction? And don't forget, Wednesday, the lab is due. Sometime tomorrow, I already graded the lab you handed in last week, and I'll upload those grades to D2L. Remember, if you ever want to question, why did I get the score on a test? any problem or why did I get the score on a lab, always feel free to see me after class or during my office hours. Because in my world, there's no such thing as a dumb question, including why did I get these points or only these points? Like I said, these 4 reactions are some of the more challenging you'll do this whole semester. But they're ones Mother Nature uses for carbohydrates. Remember, any problem I go over, always feel free to ask if you question, why did I do this or how does it work? All right, I think everybody's done. So let's do it. Look at a molecule. By the way, I was going to say, I'll sound like a broken record, but how many of you have ever even seen a record that you play music from? But anyways, I'll keep on repeating it because it's so important to look at a molecule, look for what's different. What's not carbon or hydrogen? Ooh, oxygen here, this carbon. And each oxygen, there are groups. And this carbon here, which is this carbon here, I have carbons here and here, R prime, which could have been a hydrogen, but it's not, and R double prime. It just so happens in the ring, R prime and R double prime are connected together. And when you react that with water and acid, what's attached to the carbon with the 2 oxygens, R prime or hydrogen, R double prime, because you don't break carbon-carbon, single bonds. This carbon right here will now have oxygen double bond to it, a carbonyl. And you'll get back from this right here 2 of the alcohol. If you want to write it 2, you could, you don't have to. So here's this carbon. What's attached to it? The ring and my methyl group. That's this carbon here, which is this carbon here, and it's double bonded to oxygen. Then my R group on my alcohol is ethanol. And for those who must, you could put it 2 there, but you don't have to. Either way, with or without, I would grade it correct. And that's how you do it. Now, like I said, these are challenging reactions. This one and the previous 3. And I will never on a test or a final put a synthesis problem because that's not fair and I don't teach that way. Now, the next reaction, let me make sure I'm correct about it. Yep. The next reaction involves Dr. White's hero in organic chemistry, and that's the great French organic chemist, Victor Grignard. And Victor Grignard, Dr. Grignard, everybody just calls him Victor Grignard, he discovered a couple of things that, let's see if I can find this really quick. All right, everybody see Wikipedia on there? What a mustache. I love it. And that's Victor Grignard. If you notice, his work was about 1900, 1920s. And for his work, he won the Nobel Prize. And let's see what year, if I can think, it was somewhere around 1910 or thereabouts. 1912. He won the Nobel Prize for his work. What was his work? Well, there are two steps I have to teach you about. And the first one is making the Grignard reagent. And relax, this is a fun reaction, which I've used in my research when I was at Michigan State. And the Grignard reagent, named after him, is you take an alkyl halide where X equals chlorine, bromine, or iodine, and you react it with magnesium, and you form this Grignard reagent. And that's called the Grignard reagent formation, or just making the Grignard reagent. Nope, wrong thing. And here again, X is chlorine, bromine, or iodine, those three halogens. Now, it's important that the carbon with the halogen has the magnesium, and the magnesium is bonded to the halogen. And I marked this wrong because it is. See, it even says it on the screen, it's wrong. So don't write it this way because I'll give you 0 points. And let's do a Grignard reaction. And this is such an easy reaction to do in the lab. We don't do it at ECC in this class, but I've taught it in a 2-semester organic. And we look at what's different. Ooh, carbon, carbon, carbon with a halogen, RX. Ooh, magnesium metal. And X can be chlorine, bromine, or iodine. And you form the Grignard reagent. And what's R? N-propyl. The carbon with the halogen is the carbon magnesium is bonded to. We don't break carbon single bond, excuse me. And R is this. And then I have magnesium. And what's the halogen? Bromine. And that's the Grignard reagent. Fast, easy, and you'll learn not today. When you make it, it's very powerful. And let me give you one to try. I've actually done this reaction in my research for my PhD because I needed that. What would be the product or products for the following reaction? All right, I think everybody's done. Let's take a look at this. What's different? What's not carbon? What's not hydrogen? Oh, a halogen chlorine on a carbon. Here's my R group. And X can be chlorine, bromine, or iodine. Isn't this an easier reaction? You can say no, it's allowed. And you get the Grignard reagent. And what's our isopropyl? The carbon with the halogen is the same carbon with magnesium. And then bonded to that is my halogen chlorine. And you've made that Grignard reagent. And I've used that actual one. Oh my goodness, I just looked at the clock. We're almost done. I'll let everybody copy that down. Everybody got that down? All right, if not, come back before you leave and I'll bring it back. Well, we're out of time. Time flies when you're having fun with ketones, aldehydes, and all sorts of things. Now, on Wednesday, I will start out doing the epoxide and ether and epoxide problem set. Also on Wednesday, we'll do our lab. Don't forget the lab you did last week is due this Wednesday. And we'll continue on. We're almost on track for all the time we lost, but things are looking good. With that, don't forget tonight from 5 to 6:15, I have my office hour, and I will now say, Gang gesund. Bye now. I stole that from Granny and the Beverly Hillbillies. Bye.